Hi, yes, I'm ready to begin. So hello everyone. My name is Anastasiia Lukianenko. I'm working as a software engineer at EPAM, and I hope everyone is here. Yes. Is my sound okay?
Yes, we can hear you.
Okay. So we work to make Xen for automotive domain. For that, we partnering with companies like Renesas Electronics and others. I want to introduce work of our team, which includes valuable contribution of my colleagues, Alexander Andrushenko and Andrei Anisov. We implemented Xen Guest ARM64 board support in UBoot with paravirtualized block and serial drivers. This board is to be run as virtual Xen with UBoot as its primary bootloader. The rationale behind introducing this board is better and simpler decoupling of guest from initial privileged domain, which starts guest virtual machine. So there are cross dependencies between DOM0 and guest, such as DOM0 needs guest kernel to boot it. And this kernel, which comes from the guest OS, doesn't belong to DOM0. This can interfere if a kernel or guest OS needs to be updated. But we can avoid these cross dependencies between domains by using UBoot, which doesn't know about the core inside the domain and it comes from. Those DOM0 doesn't know about the guest domain internal structure, which makes updating and tuning the guest OS much easier. As an example, I'll talk about Android. Recent Android releases become more and more complicated with respect to disk partitioning and security. This requires signed binaries, slotted approach to system updates and boot, etc. Another example of guest OS is our case in which we use CinDOM0 and initramfs. We have guest kernel inside the rootfs, which make rootfs much bigger and complicates the updating of guest OS. The process consists of putting new kernel into the rootfs, repacking and signing it. With UBoot, all the above issues go away unless any part of it, including UBoot, need to be updated. Now let's see how generic bootloader UBoot helps. There are cases when not only Linux kernel changes for the guest, but also the way it partitions the disk. Such a change may require that Excel's virtual disk configuration as well. Having a unified bootloader in domain 0 allows to handle changes in guest configuration by the guest itself. Also, UBoot has ability to run scripts similar to bash, which allows to execute certain commands in guest domain. These scripts are on guest virtual disk. And this way, guest can make changes by itself. Talking about new versions of guest OS, we need to remember that there are specific information which needs to be present in device tree nodes. But provides device tree only with essential information. This device tree consists of information given by Xen and domains Excel configuration. That's why we need to use device tree overlay mechanism. As we can see on the picture, loading device tree has three main stages: building, partitioning, and running. Device tree source use device tree compiler DTC to compile it into device tree blob DTB. This device tree blob stored in unique or boot partition, and stage is loading DTB from storage memory and start kernel from the memory address of the loaded device tree. Now let's talk about Xen support for UBoot. Xen support for UBoot implemented by introducing a new Xen guest ARM64 board and porting essential drivers from MiniOS, as well as work previously done by NXP, which includes PV block device, which receives notifications from event channel, grant table in which shared memory described, dynamic RAM size. We use it because when we work as a guest, we don't have memory sizes as UBoot usually has. So the size defined in the device tree instead of statically values. Xen Store and xenbus responsible for device discovery and configuration. And also we use position-independent code because we cannot statically any start address and at compile time because Xen chooses it at runtime. So we added support for Xen paravirtual device as a UBoot driver with respect to its driver model. In UBoot, there are two ways to attach device to driver. The first way is to describe it in device tree, and the second way is to describe it as a device instance structure in UBoot. Both methods are not suitable for us because we create devices dynamically based on Xen Store information. For that, we implemented Xen Store device enumeration and create devices dynamically. Initially, we tried to make a U-class BLK device, which is already in UBoot, but we didn't succeed with that because of UBoot driver model specifics. When we go into details, we see that PV block driver must be a parent device and PV block BLK device must be its child. This implementation is needed to comply to UBoot model architecture. In other words, parent device handles the actual device access, while its child uses parent as a transport level to exchange information with the backend. So for that reason, we created a new U-class block class for paravirtual block devices. Moreover, we need to remember that UBoot has a variety of block devices, and predating driver model distinguish them using interface type. So we also created type PV block interface type. During the implementation, we encountered some difficulties. We uploaded our work on GitHub and received important feedback from the community. Special thanks to Julien Graal, Stefano Stabilini, Peng Fan, and Simon Glass for valuable advices. First issue we faced is tying UBoot to a specific version of Xen. We used Xen 4.13 version headers, which has a stable ABI. But if we think about using UBoot with Xen 4.10 version, unstable one, what do we need to do? In the first stage, we used a copy of Xen interface headers and Xen define, which set UBoot to a specific version of Xen. And the question was, is it possible not to use it? Because UBoot may require the headers matching to actual version of hypervisor. So the answer is yes. We created a subset of headers with only stable ABI and no Xen version dependency. The next difficulty was reaching inaccessible memory regions for MMU. When we do a page table for MMU, we need to communicate with Xen to know what memory regions are available. It happens before you set up. And some of these regions are available in device 3, but the memory pages that are used for console and shared memory are not available. To get these addresses, we need to communicate with Xen. And then for ARM, there is such that pages must have certain attributes. And the problem is that before MMU setup, we worked with the cache turned off, but Xen thinks that the cache turned on. And when we write in memory, Xen cannot see these records because Xen reads from the cache, not from the memory. So we have to maintain manually until the MMU setup. The third problem was guest magic base address. Guest magic base address is the address that is used as specific memory region. UBoot is not able to dynamically update the page table for MMU. UBoot needs to statically register all the mappings because UBoot doesn't know how to do map and unmap. Initially, we took guest magic base address as a constant, defined size, mapped the MMU for these parameters. After discussions, we decided to use the hvm op getParam hypercall, which allows us to find out from Xen where the shared page for the console and grant table will be located. As a result, we don't use guest magic base address and have generic solution. Next difficulty is position independent port. Sorry. UBoot normally requires the boards to run without position-independent executables. For example, the final binary is not easily relocatable and linked to run at specific address. It means that we must know Xen's memory internals to properly build. We cannot statically define any start addresses at compile time because it's up to Xen to choose it at runtime. Fortunately, UBoot for ARM64 has a PI support and we can rely on that. Fifth issue is fifth issue is console absence. The serial console is made in form of paravirtualized driver, so the moment when it can be used occurs after the MMU setup and serial initialization. Therefore, we do not have early console. We can implement a driver or such, but it seems too much for the final goal. Also, we can use hypervisor I/O plus console I/O write, but it's not an option as it requires specific privileges to be used. Last problem is single RAM bank supported. So when we create a domain, Xen can do 2 memory banks. First one is 3 gigabytes memory, 3 gigabytes of low memory. If more memory is given, then Xen makes another memory bank in high memory. UBoot most likely doesn't require 3 gigabytes of memory for its work and launching OS. So it's enough to take one bank of memory and define and work with it. It's important for us to know that number of banks because it affects the work of UBoot in the runtime. The number of banks depends on the domain configuration, which we don't know. Therefore, we decided to use one bank of 3 gigabytes, which should be enough. Now I want to show you demo. I will share my screen for that. Okay, I hope you'll see it. We create a guest domain. Then we use pvblock info command to show info like vendor type, capacity. Then we use xt4ls command to show directories, and then we run pvblock boot. Kernel starts. We successfully log in, and that's all. Some problems with webcam. Oh, now it's okay. This work was upstreamed and discussed, so we are almost ready to push a second version of it. You can see its status by clicking the link here. So thank you for attention. Now you may ask questions in chat or using audio. For the front-end implementation, did you use utilize the front-end handler classes in libxenb? No. You're welcome. Any other questions? Okay, thank you for being here. Goodbye.